You've seen the animations 1,000 times. A sleek rocket touches down on the red dust of Mars. The astronauts step out, and when they're done, they just fire up the engines and fly safely home. It looks as simple as driving out to the country and turning your car around. That's how it works, right? Wrong. A trip to Mars is a one-way physical trap. Today, we are going to explore a brutal, beautiful law of nature that Richard Feynman warned us about, one that will completely change how you see every rocket launch from now on. Think about your everyday life. You drive to the grocery store, you buy your food, you put the car in reverse, and you drive back home. The road is exactly the same in both directions. It takes the same amount of gas to go there as it does to come back. This is the symmetry we grew up with. It is completely baked into our biology, into our deepest intuition. Throw a ball up in the air. What happens? It comes right back down into your hand. What goes up must come down. So we look up at the night sky, we point at that little red dot, and we think of it as just another destination. Just a really long road trip. You pack enough supplies, you build a big shiny engine, you fly there, you plant the flag, and then you just turn the ship around. It is the ultimate American dream, is it not? The great frontier. We conquered the oceans, we conquered the moon, so of course, we will conquer Mars and come home to a giant parade. It is completely natural that you think this way. You are not foolish for believing it. Every science fiction movie, every shiny corporate space animation, they all sell us this beautiful, perfectly symmetrical dream. They show us the massive rocket taking off from Florida, the triumphant landing in the red dust, and then the return trip is just quietly assumed. It is skipped over in a quick, triumphant montage. We naturally assume that the physics of coming back are exactly the same as the physics of leaving. We look at space, and we just see empty distance. A flat void that you just have to push through, as long as you push hard enough. But here is the problem. Space is not an empty highway. And gravity is not just a simple string pulling you down to the ground. Gravity is a landscape, a deeply uneven, invisible geography that you are currently trapped at the very bottom of. When you leave Earth, you are not just driving down a flat road. You are doing something violently unnatural. The universe does not play by the rules of our comfortable paved roads. So, if it does not work like a highway, what are the real rules? Think of gravity not as a downward pull, but as a deep, steep valley. Right now, you and I are sitting at the very bottom of the Earth Valley. To get a spaceship out of here, you have to push a gigantic, unimaginably heavy rock all the way up the side of this mountain until you reach the flat top. It takes a violent amount of energy. But on Earth, you are not pushing the rock alone. You have a massive advantage. You have an entire industrial ecosystem standing right behind you. You have thousands of engineers, giant liquid hydrogen refineries, power plants, and global supply chains. You have a whole civilization working together to push that huge rock up the hill. And it works. With all that muscle, you heave the rock over the edge. It drifts across the flat plane of space, and then it rolls down into another valley. It settles at the very bottom of a new hole. That is Mars. Now, you want to come home. You have to push the rock back up the Martian hill. The gravity is a bit weaker, sure, so the hill is not quite as tall. But look around you. Where is the infrastructure? Where are the giant fuel refineries? Where are the power grids and the thousands of engineers? There is nothing. Just you, your heavy rock, and an endless desert of freezing red dust. The entire support system that got you out of the first valley is millions of miles away. So, what is the solution? How do you get the rock back over the edge? The logical answer, the one everyone immediately jumps to, is simple: just bring the pushers with you. Pack all the fuel you need for the return trip while you are still on Earth, carry it all the way to Mars, and fire it up when it is time to go home. It seems so incredibly obvious. But here is the problem. You think you can just carry your own fuel to climb back over that barrier? That is exactly where the catastrophe begins. Let's say you decide to bring the return fuel with you. You want to carry just 1 extra kilogram of fuel to Mars, safely storing it for the trip home. Sounds simple enough, but fuel has mass. It is heavy. To push that 1 extra kilogram up our giant Earth hill, you need fuel to lift it. Let's say you need 10 kilograms of fuel to lift that 1 kilogram. But wait, now your rocket is 10 kilograms heavier before it even leaves the launch pad. So you need more fuel just to lift the fuel, that is, lifting the fuel, that is, lifting your 1 extra kilogram. This is not simple addition. It is a runaway nightmare. It is a mathematical catastrophe. Physicists call this the tyranny of the rocket equation. Have you ever watched a rocket launch? Really watched it? It is not a graceful bird taking flight. It is a violently shaking, controlled explosion. As it roars into the sky, huge pieces of the ship are physically snapping off. Giant metal cylinders are peeling away and falling back into the ocean. Why? Because the machine is absolutely desperate. It is terrified of mass. It has to shed every possible ounce of dead weight just to survive the climb out of Earth's gravity. Now, imagine trying to carry an entire second rocket, fully fueled, hidden inside your first rocket, just so you have a ride back from Mars. The vehicle you launch from Earth would have to be so unimaginably massive, so grotesquely huge, that it becomes physically impossible to build. You cannot just pack a return ticket. The universe does not allow it. The math does not just add up, it multiplies exponentially until it crushes your entire plan under its own weight. So, if bringing fuel from Earth is a physical impossibility, you are left with only one other option. You have to make the fuel once you get there. But is that really any better? So, carrying the fuel is a disaster. What is the alternative? In situ resource utilization, ISRU. It is a fancy acronym for a very simple idea: live off the land. The plan is to send a robotic chemical plant to Mars before the humans arrive. It will suck in the Martian atmosphere, mostly carbon dioxide, mix it with some water dug out of the ice, and bake it all together to create methane rocket fuel. It sounds brilliant, doesn't it? It sounds like a perfect, elegant solution. It is the kind of plan that looks incredibly neat and tidy on a whiteboard in California. But Richard Feynman, one of the greatest physicists of the 20th century, had a profound warning about this kind of thinking. He warned us not to confuse our beautiful theories with the messy, brutal reality of nature. He knew that when you look closely enough, nothing is just a machine. It is all just atoms, jiggling. Think about what we are actually asking this machine to do. We are dropping a delicate piece of Earth machinery onto an alien world. The temperature swings from a comfortable afternoon to -100 degrees at night. It is a place filled with microscopic, razor-sharp dust that gets into every gear, every seal, and every moving part. And in that brutal environment, we expect this machine to perform a delicate atomic dance. We expect it to rip carbon atoms away from oxygen atoms and then coax them to snap together with hydrogen. We are asking it to create the volatile, explosive energy of a rocket launch reliably, perfectly, for months on end, completely on its own. If a valve sticks on Earth, a technician walks over with a wrench and taps it. If a pipe freezes, someone wraps it in a heater. But on Mars, there is no one to tap the valve. There is no one to fix the heater. If the atoms stop jiggling the right way, if the chemistry fails, the fuel tank stays empty. And an empty fuel tank on Mars is not a delay. It is a tomb. We are placing all of our hope in a fragile chemical process happening millions of miles away, assuming nature will simply cooperate because our math says it should. But nature does not care about our math. Richard Feynman left us with a haunting reminder. He said that for a successful technology, reality must take precedence over public relations, for nature cannot be fooled. We can draw the most beautiful diagrams. We can render the most breathtaking animations of sleek silver ships gracefully touching down and effortlessly rising back into the Martian sky. We can convince ourselves that because we wrote the math on a whiteboard, the universe will simply obey. But nature does not watch our animations. Nature is just gravity, pulling endlessly. Nature is just atoms, locking together and pulling apart, refusing to change their state unless we pay the exact, brutal price in energy. And on Mars, the price of admission to come home is devastatingly high. When we talk about traveling to other planets, we are not just talking about an engineering problem. We are talking about fighting the very fabric of the cosmos. Every atom in your body, every molecule of fuel you burn, was forged in the blinding heat of a dying star. And now, we are asking those tiny fragments of stardust to lift us out of one deep gravity well, drift across the freezing, empty dark, and claw our way out of another. We are asking the universe to let us break its oldest, most fundamental rule, that what falls to the bottom of the valley stays at the bottom of the valley. We are trying to outrun gravity, outsmart chemistry, and build a bridge across the void using nothing but fire and our fragile human minds. So, the next time you see a video of a rocket taking off from the red dust of Mars, do not just see a machine. Look closer. See the invisible, towering mountain it has to climb. See the violent, desperate explosion required to push that heavy rock over the edge. See the terrifyingly fragile chain of chemistry that must work perfectly, completely alone, millions of miles away from the warm, safe cradle of Earth. Going to Mars is not the impossible part. Falling into a valley is easy. The hard part, the part that tests the absolute limits of physical law, is climbing back out. We might do it one day. We might actually build a fire big enough to push us back home. But if it takes that much violence, that much raw, screaming energy just to hop to the closest rock next door, what does it take to actually cross the endless sea of stars? I will leave you something to imagine. So we stare up at that little red dot in the night sky. We dream of walking on its cold, dusty surface, of planting our flags and building a second home. And maybe we will. Humans are stubbornly brilliant creatures. We might just figure out the perfect sequence of jiggling atoms. We might build the perfect machine, master the freezing alien dirt, and push that incredibly heavy rock all the way back up the Martian hill so our explorers can come safely home. But when that day comes, when that rocket finally roars to life and tears itself away from the grip of Mars, it will not just be a triumph of our engineering. It will be a triumph of borrowed power. Because every single ounce of energy we use to climb out of that deep gravity valley, the roaring fire from the thrusters, the electricity pulsing through the ship's nervous system, and even the warmth inside the astronauts' suits, none of it was actually created by us. We cannot create energy, we just rearrange the atoms. We just unlock what is already there. All of that violent, screaming power had to come from somewhere long before it was stored in our metal fuel tanks. It had to be forged, packed together so incredibly tightly, just waiting in the dark for the exact moment we needed it to snap apart and push us across the void. If you trace that roaring fire backward, past the chemical plants, past the fragile atmosphere of Earth, past the very formation of our planets, you do not find a clever machine. You find a blinding, chaotic furnace. You find a star. We spend our lives obsessing over how to build a fire big enough to cross the empty ocean of space. We worry about the brutal math of the rocket equation and the cold, unyielding rules of gravity. But walk outside tomorrow morning and just feel the warmth on your face. The sun is sitting right there, burning furiously in the absolute zero of space, pouring out more energy in a single second than human civilization could use in a million lifetimes. How did all that fire get trapped inside that massive, glowing sphere in the first place? What unimaginable force is holding that ultimate, endless explosion together, keeping those atoms jiggling so violently without just flying apart into the dark? Well, that is a different story. I will leave you something to imagine.